Hi all. Today we are going to give a presentation on prediction of warpage and its control mechanism in panel level advanced packaging. We are group number 2, myself Nitin Krishna, and other group members are Siddesh Vishambar, Mayur Murray, and Konal Suneshwari. Our problem statement is uh, the challenges posed by warpage in manufacturing process involved in fan-out panel level packaging. Advanced semiconductor packaging is moving towards fan-out wafer-level packaging and panel-level packaging to achieve higher I/O density, smaller form factor, and lower cost. However, these technologies face a fundamental thermomechanical challenge, which is warpage. Warpage arises because of the difference in CTE among the constant materials. We know the constant materials are silicon, copper, maybe glass, dielectric polymers, and epoxy molding compound. All these materials are having different coefficient of thermal expansion, and when it heats up and cools down, this difference in CTE causes the thermomechanical stress inside the package, which is stick together. Not just the stress caused by difference in CTE, there is another kind of stress which is involved because of the chemical shrinkage during polymer curing. This happens when a polymer is cured and it shrinks, and this will also lead to warpage. And this also amplifies the deformation which is caused in the panel level packaging. For a panel level package, the problem is especially severe. For a Gen 3 package, for example, the dimensions are 550 in 650 mm, which has 5 times the area of a 12-inch wafer. Warpage can exceed approximately 40 mm after debonding, which is a huge number if you see. And such deformation is what prevents panel from being handled, aligned, and processed further, making warpage the primary barrier in FO PLP industrialization. So our presentation covers the fundamentals of warpage, what causes it, how it is measured, and how it can be predicted using analytical, computational, and artificial intelligence based methods, and what design strategies can use to suppress it. So let us first look at what exactly is warpage. So warpage is the out of plane deformation of a substrate, wafer, or a panel which is caused by the residual internal stresses. It is quantified as the maximum deviation from the reference flat plane, as you can see in the figure which is given in the slide. And usually warpage is represented in a length by length unit because it makes sense only when we say I had this much warpage in a this much length scale. So that in different length scales, same warpage does not create the same impact. So always warpage is represented by length unit. And about the warpage orientation, the standard defines two shapes. A convex shape, which means center is higher than the edges and the cross section looks like a frown. A concave warpage means edges are higher, the cross section look like a smile. The sign can flip between the process steps as new layers are being added or some other processes are being carried out. The main impact of warpage in manufacturing is this can cause misalignment during lithography, which is very sensitive process, and die placement. Also prevents vacuum chucks from gripping the substrate, which leads to interconnect shift in distribution layers and can induce cracks. It can also lead to delamination, solder joint fatigue, and in extreme cases, the fabrication process simply cannot continue because the equipment cannot handle the warped substrate. So, when we look at the root causes for the warpage, CTA mismatch is the primary and most important reason. because every material in the package stack has distinct coefficient of thermal expansion, which, as given in the slide, silicon is having around 2.8, copper is having around 17, and polymer is having around 39 to 55 parts per million per degree Celsius. So when the assembly cools down from a process where temperature was higher, material with higher CTE try to contract more than those with lower CTE. Since the layers are bonded together, this difference in contraction generates internal bending moment that warp the structure. Other than CT mismatch, another important point which I mentioned earlier was curing shrinkage of polymers. So, epoxy molding compound and dielectric resin undergo irreversible volumetric shrinkage during cross-linking. And this chemical contraction is independent of thermal effect and adds directly to the residual stresses. And this is something which we need to keep an eye on, because without considering this, and if you're trying to model warpage, it can lead to an error approximately around 27 percentage, which shows the importance of considering curing shrinkage while modeling warpage. So the warpage of the final structure does not just depend on the final condition, it actually depends on the processes it has been through. Means the process, it is a process path dependent factor. So it is not just determined by final layer stack alone. Each layer deposited or cured at its own temperature and stress-free reference point differs for every material. So the total warpage is a cumulative result of all preceding thermocycles, making process sequence modeling essential for accurate prediction. Fan-out packaging, as we are aware, is some different kind of packaging which is happening in the wafer or panel level, where the routing area extends beyond the die using redistribution layers, which are built on reconstituted wafer or panel. So there are two common process approach which exist in fan out packaging. One is chip first approach and other one is RDL first approach. There are other approaches, but these are the two important approaches. And in mole first approach, we have a phase down approach and phase up approach. So essentially, the difference is in chip first approach, the die and the TSV interposers are fabricated first, followed by the glass carrier attachment and multiple RDL dielectric layers. In RDL first, that is die last approach, RDLs are built directly on a glass carrier, then chips are bonded and overmolded over the carrier, overmolded before the carrier is removed. So both approaches suffer from warpage, but the scale of the problem is dramatically different between the wafer and panel format. So that's what's the main difference between the wafer level packaging and panel level packaging. You can see it in the table by yourself, because the difference between wafer level packaging and panel level packaging is huge, because the area first of all is much more than wafer for a panel, and the warpage number for a wafer is much lesser compared to panel, and the gravity effects are negligible for wafer while it has to be considered for a panel level packaging. And the primary advantage of wafer level packaging is the mature process ecosystem, because this wafer has been used for semiconductor fabrication, RDL fabrication, everything. So it has a mature process ecosystem, but panel level packaging does not have that. On the other hand, it has having higher throughput. So these are some of the important differences between wafer level packaging and panel level packaging, and shows how important warpage is in panel level packaging compared to wafer level packaging.
Hello everyone, my name is Siddesh Vishwankar and I will discuss about measuring warpage and introduction to FE. To start by looking at how we measure warpage accurately, we rely primarily on non-contact optical methods to avoid altering this delicate substrate. For a standard 12-inch wafer, optical profilometry using infrared interferometry is the best standard. It bounces infrared light off the surface to generate detailed contour maps with micrometer resolution. It complies with JEDEC standards and allows us to watch warpage evolve inside the heating chamber. But as we scale up to massive fan-out panels, we shift to shadow Moore's interferometry. This method projects a reference grating like of a grid of fine shadow onto the substrate. As the panel warps, it distorts the grid, creating a fringe pattern. The software analyzes this to calculate exact displacement, making it ideal for multi-point data on large areas. When panel exceeds our equipment's physical limit, we use a practical fallback, measuring height difference at the lifted corners with a height gauge on a flat surface. However, physical measurements has limits. High resolution at a large scale is difficult, and elevated temperature setups are expensive. Most crucially, there is the gravity effect. When you lay an ultra-thin flat panel, its center sags under its own weight. This conflicts with process-induced thermal warpage, masking the true deformation. Because of these physical limits, advanced simulation methods are critical. Moving on to the next slide, to mathematically predict this warpage, analytical methods are our starting points. When simulating redistribution layers, or RDLs, meshing every tiny copper trace and via is computationally impossible. Instead, we use homogenization, treating the complex copper dielectric layer as single, uniform composite material. We calculate the effective CTE using Shapley energy-based method. Because these structures are anisotropic, we calculate the out-of-plane CT and in-the-plane CT, factoring in Poisson's ratio to account the mechanical responses across the planes. And for effective stiffness, we calculate the effective Young's modulus. With these effective properties, we apply plate theory to estimate the actual workpage curvature, denoted by kappa. This curvature is driven by thermal bending moment, which represent the stresses caused by temperature changes interacting with mismatched expansion rates integrated through the panel's thickness. While these equations are elegant and fantastic for quick sensitive checks, these cannot capture geometric nonlinearity or the sequential step-by-step stress accumulation of the actual manufacturing process. For that, we turn to finite element modeling. Finite element analysis, or FEM, is our primary workhorse because it overcomes those analytical limitations. It handles complex geometries, nonlinear viscoelastic material, and sequential manufacturing steps. The workflow is meticulous. We build a 3D model of layers, stack, assign temperature-dependent material properties, apply thermal profiles that replicate the exact factory heating and cooling cycles, and solve for equilibrium deformation at every step. Because this requires massive computation power, we use two major optimization techniques. First, we exploit the symmetry. If the panel layout and structural behavior are symmetric, we only model one-fourth of it, cutting the computational cost by 75%. Second, for ultra-thin substrate, rather than using 3D solid elements, we create a shell element so that we can reduce the computational time without sacrificing the warpage prediction accuracy. So what actually a FEM solver is computing? It starts with thermal strain. At each load step, the solver calculates strain using epsilon is equals to delta T equation. But the delta T has a crucial part, that is the reference temperature. There is no single global reference temperature for overall panel. Each individual layer has its own reference temperature based on when it was deposited or cured. Next, it calculates the mechanical stress. This equals the stiffness tensor multiplied by the by difference of total and thermal strain. For rigid materials, this stiffness tensor is the linear elasticity. But for epoxy molding compounds, which creeps and relaxes over time, we use the generalized Maxwell model to capture its viscoelastic behavior. To balance these forces, the system enforces static equilibrium. The stiffness matrix time displacement equals the thermal forces plus the gravity. Importantly, we enable geometric nonlinearity. When a large panel warps, its structural stiffness actually shifts. The solver recalculates and updates the stiffness matrix every single iteration to reflect the newly warped shape. Finally, we apply the boundary conditions. Alongside pinning a center node and applying symmetric constraints, we address the gravity issue we discussed earlier. To mimic a panel resting on a factory workbench, we model a rigid table surface beneath the virtual panel, define a contact pair, and apply a 1G body load in the Z direction. This gravity boundary condition ensures our simulation perfectly captures the real world side.
Hello everyone, I am Mayur. This slide explains the element birth date technique. Since layers are added sequentially in real manufacturing, the simulation also activates elements step by step. Initially, a dead element is given extremely low stiffness and it carries no load. Once that layer is deposited and cured, the element is born, meaning its stiffness and loads are restored to its current temperature. Warpage is mainly develops due to the CTE mismatch between the materials such as silicon, copper, dielectric and EMC. As thermal loading occurs during processing, incompatible thermal strain build up and that causes the bending. The figure at the bottom shows warpage evolution through different fabrication stages. The process starts with the RDL fabrication on a glass carrier, followed by the molding and finally debonding. Each contour plot represents the deformation at a particular stage. As layers are added and temperature changes, the stresses accumulate and deformation also evolves. An important point that is the warpage direction can even reverse. After debonding, the glass carrier constraint is removed, making the structure more compliant and leading to large deformation. The simulation sequence on the right summarizes the steps. Here we start at the room temperature, we heat it to about 125 degrees Celsius for EMC curing and then activate the corresponding elements. Then we again cool back to the room temperature where the residual stresses develop due to CT mismatch. Then we apply the post-mold cure, during which viscoelastic relaxation in EMC reduces the stresses. Finally, debond the carrier, then releasing the constraint and causing major stress redistribution and maximum warpage. Overall, this stepwise activation with thermal cycling captures the part-dependent behavior of the package. So in this slide, we will explain the material modeling strategy used to capture the thermomechanical behavior accurately in the simulation. So materials like silicon, copper, glass are modeled as isotropic linear elastic materials. So they follow Hooke's law with constant Young modulus and Poisson's ratio. This assumption is valid because their properties remain stable within the process temperature range. For the RDL layer, instead of modeling individual copper traces and dielectric regions, a homogeneous approach is used. Effective properties such as modulus and CT are calculated using the volume fraction based mixing rules. This reduces the computational cost while it's still preserving the thermomechanical response. The main complexity comes from the epoxy molding compound or EMC, which behaves viscoelastically. Its stress response depends on the both strain history and temperature. To model this, a generalized Maxwell model is used, where multiple spring dashboard elements represent different relaxation time. It helps us to capture the stress relaxation during thermal cycling and post-mold cure. The temperature dependence is included using the WLF equation, which we can see in the slide, which shifts material behavior relative to a reference temperature. In addition, the curing induced shrinkage is accounted for through an equivalent CTE correction. This combines the thermal and chemical strain effects, explicitly modeling the cure kinetics. As shown, the corrected CTE is significantly higher, which strongly affects the warpage prediction. Without this correction, the warpage is over-predicted, which we can see the two images provided in the slides. On the left side, the warpage is over-predicted, and on the right side, the lesser warpage is shown. So while the corrected model gives more realistic deformation results, finally for the composite system, the effective CT is obtained through volume fraction averaging. So the overall response depends on the relative proportion of copper and dielectric materials. This slide explains how we reduce the warpage using parametric studies and optimization. The goal is to identify the most influential design variable and to find their optimal combinations. First, it is the response surface method, which is RSM. So here, the warpage is expressed as a function of variables like CT, modulus, and thickness using a polynomial model. By taking its derivatives, we can directly find the optimal point. This makes it computationally efficient when full simulations are very costly. The next is Taguchi design of experiments. Instead of testing all the combinations, we use orthogonal array system in this method. For example, an L27 array reduces 729 simulation to just 27, which is huge. So while it's capturing the key effects, so it's very effective for screening and sensitivity analysis. The third approach is CTE modulus co-optimization. So here we reduce the stress by matching the CTE with copper and use a lower modulus material to allow stress relaxation. So now coming to the results, the RSM gives about 33 to 36% reduction in warpage. Taguchi keeps the warpage below 7 mm across the steps. The CTE modulus matching gives up to 48% reduction in the curvature. So finally, we coming to the plot. It shows the warpage versus CTE. In the first, increasing CTE reduces the warpage due to lower mismatch with copper. In the second, we can see the one minimum point where warpage first decreases and then increases. So the minimum point corresponds to the CTE matching, where the mismatch strain is the lowest. There is an optimal CTE, not simply higher or lower, and that's what the optimization target is.
Okay, so now I will discuss a very important factor that is often overlooked in warpage prediction, that is the effect of gravity on panel warpage. Most models focus on thermal effects only, but this study shows that gravity also can significantly change the final observed warpage. So the question comes, why gravity matters? So large and thin panels experience self-weight deformation. In conventional FEM simulations, we actually consider only CT mismatch, which leads to thermal bending. However, these models ignore gravity, and as a result they tend to overestimate warpage. So to get realistic predictions, gravity must be included. What are the limitations of conventional models? Traditional models assume that warpage is caused only by thermal mismatch, but in reality there is an additional mechanical effect, that is gravity. So because of this missing factor, simulations predict much higher deformation than what is actually observed. So on the right side we can clearly see the simulation results. The first case shows warpage due to CTE mismatch only, and the second case includes the gravity effect. The deformation becomes significantly smaller when gravity is included. This happens because when there is only effect of thermal mismatch, and we say if panel bends upwards, say convex, so there is a large warpage of 28 mm. But when gravity, that is included after debonding, then there is a downward bending, say sagging. So due to this combined effect, they oppose each other and the net warpage reduces to 1 mm. So the most important takeaway from this slide is warpage has been reduced from 28 mm to about 1 mm, which is nearly a 97% reduction after debonding. So why this happens? This happens because two effects are counteracting each other, that is the thermal mismatch, which causes the panel to bend in one direction, and gravity causes it to sag in the opposite direction. Another key point is that the effect of gravity depends on the process stage. During molding, the structure is thick and stiff, so gravity has minimal effect. But after debonding, the panel becomes thin and flexible, so gravity becomes dominant. This is why the maximum reduction is observed after debonding. So, including gravity in simulations has a major impact. It makes predictions closer to real experimental values, and it avoids overestimation of warpage. So, gravity does not eliminate warpage, but it reduces the observed deformation by counterbalancing thermal effects. Therefore, for accurate warpage prediction in large panel level packaging, gravity must be included in the modeling process. So now coming on to the next slide, let us see that how we can control and minimize warpage through design and process optimization. So in this slide I will explain four key aspects of warpage control, that is material, structural, process optimization and advanced optimization methods. So first, at the material level, let us see. CTE matching between glass and EMC helps to reduce thermal mismatch, which directly lowers warpage. Using CTE matched interlayers reduces interfacial stresses. And a high modulus EMC increases stiffness, which will prevent excessive deformation of the panel. And low shrinkage resins reduce residual stresses formed during curing. So proper material selection is essential to control internal stresses. So next, structural optimization. It focuses on geometry mainly. So a thicker glass carrier reduces warpage during processing stages. Increasing chip and thickness, overall thickness improves stiffness, which reduces final warpage. Reducing copper volume fraction to around 20% helps minimize CT mismatch. And for very large panels, partitioning into smaller sections helps control deformation. So the idea is to increase stiffness and balance the structure. Now coming to process optimization. Include what should we do while doing the simulation. Including curing shrinkage improves prediction accuracy. And modeling gravity reduces warpage estimation error, as we discussed earlier. Using a viscoelastic EMC model helps to capture stress relaxation during curing. Shell elements can significantly reduce computation time, and especially for thin structures. And AI based models allow faster design exploration. So accurate process modeling is crucial for a better simulation result. Finally, advanced optimization techniques. FEM provides accurate results but is computationally expensive. Methods like Taguchi and response surface methodology (RSM) reduce the number of simulations that are needed. And whereas AI models enable fast and efficient prediction with high accuracy. So these methods help balance accuracy and computational efficiency. So warpage cannot be minimized by a single parameter. It requires a combined optimization of material, structure and process. So this integrated approach is essential for achieving accurate prediction and a good package design. Now, this was our whole project, and these are the references which we have used, and this was about our project. Thank you.